Eli the Iceman. But that's for later. All right, so to answer this question, what's the direction of the force on Q?
What does the B stand for?
Magnetic field. -4 Tesla in the K hat direction. Whereas defined over there, K hat is coming at you.
Is that a -2 C?
That's a positive 2C. That is the charge, 2 coulombs.
Is that the direction of force?
Yes.
Okay.
Pardon?
24.
That's not a direction.
Is the direction of force? Or that's just the way I don't move, not the direction of force.
So you're going off a previous example as opposed to other ways of doing it?
Well, I thought, I don't know, based on this previous example, yes. I thought if they're the same side, they would move down. If they're the opposite sides, they move up.
Same sign.
The sign of the electric field.
There's no
the sign-
electric field.
Or not the
That's
electric
drawn
field, the
in.
magnetic field.
Okay, so the magnetic field is into the board.
I think it's like the opposite of the previous one we did. So previous one we did, we had a positive electric field.
Is it 4 Tesla or -4 Tesla?
That's -4. The electric fields aren't drawn here. I can draw an electric field, but I think that would just
sorry,
confuse you.
The magnetic field we had in the previous question
Okay.
was positive. This magnetic field is negative. So I think that's gonna change how the charge reacts with the field. So I think it would, because that way. Because if into the board round like that, it's going this way. Magnetic field.
Anyone else? Of course, I mean, it ultimately you have a choice of 6 directions if you just want to do a random guess. But
Well, I found
what that
My money's up that way.
that way? Okay.
I found force is 24 newtons.
Okay.
It's positive. What is that? But I'm not. But we didn't know what positive that means. What positive means in this case.
So how'd you get positive?
QVB, because it's -2.
Say it again?
QVB,
QVB,
which
okay.
is -2 times -4.
Where'd you get the -2?
Is the charge of the.
That's a plus sign right there.
Oh.
Although it kind of looks like a cross, but it's supposed to be a plus sign.
Did you say the X's mean the magnetic field is into the board?
Yes.
So my thinking is because one is negative and one is positive, they'll attract each other because that always works. And so it'll curve like inwards, like towards the edge of the board. Or it could go out before that. Yeah, I think it's gonna go, it's gonna work out.
You've narrowed it down to two of the 6 directions, which may or may not be correct.
We're just going outwards.
I'm not quite sure which outwards.
Well, the last, magnetic field we had, the charge is moving towards like the center. So what I
Right.
see, it's like it's moving out of the center.
Out of the center. So, as in it's gonna be sort of repelled in some direction like that? All right, here's a hint. You mentioned QVB. What is the actual formula?
QV cross speed.
And so I got a cross product in here. What do you know about the vector produced by a cross product in terms of direction?
Perpendicular.
To
The other one.
other one?
The, they're perpendicular to each other.
Or there's 3 vectors involved here.
Right, okay, so it's the, it's, the vector from the cross product is perpendicular to the third vector, for being the charge.
Charge is not a vector.
Yes.
Perpendicular to the first vector.
Perpendicular to
First
what?
vector.
First vector? Not 100% there. Oh, it's been so long. I assume you were studying physics every day.
Oh. This wasn't supposed to be
Just different physics.
different. 151.
The vector product is perpendicular to both of these vectors. So, assuming it's not 0. If V and B are parallel to each other, the cross product is 0. But so I have a magnetic field that's going into the board, I have a velocity that is going that way. Therefore, what are the 2 directions that are perpendicular to both of those vectors?
The opposite.
J hat up.
Okay, it's up or down. Those are the, so let's narrow it down. It's either gonna be up or down. Because I'm asking when it enters the uniform magnetic field, not after it's been there for a while. All right, if we do it by cross product, do it the math way. The direction of the force is gonna be equal, well, that's a positive number. V is +3, actually, it's just doing directions, positive I hat, cross B, which is negative K hat. So I'm now down to negative I hat cross K hat. Negative just factors out. I cross K.
J.
Why do you say that?
Well, it's just, it has to be perpendicular.
Yeah, why is it not negative J?
I hat, K hat, J hat, negative I hat. Negative J hat.
Is this,
I cross K is negative J?
So negative I cross K. Well, it's
Is,
negative.
okay, so I wasn't sure if you're bringing that negative sign in yet.
Yeah, no, I'm bringing that in.
So you're saying that I cross K is J?
It's J hat, and then it's going to be negative J hat being.
And why do you say I cross K is J?
Because it, like, there was a pattern that we followed, there
Yes.
was like, J hat, yeah. I cross, okay, then, wait a minute, hold on, getting there, not at all, wait a minute, what happened? Or, doesn't matter, so, does matter about if I do K cross I?
K cross I is the negative of I cross K. Commutative property does not hold.
Oh.
The order matters.
Wait, so if K cross I is the negative of,
It's almost there, it's floating around in there somewhere.
if that's the negative, wait, no, if K cross I is then J,
K cross I is J.
K cross I is J, then the opposite of that would be I cross K is negative, or negative J.
So that's negative J hat, which ends up being a positive J hat in the end. It's forced upwards. What I believe Ibrahim was trying to recall is that if I go in order I, J, K, if I go in that order, it's positive. I cross J is K, J cross K is I, K cross I is J. If I go in opposite order, it's negative. In this case, I had I first, then K, so I'm going to the left, so I'm gonna get a negative. Then there's the right-hand rule. Years ago, I'd given a test, a 252 test, and I had too many of these on there for the time, but I had a whole bunch of ones where you have to use the right-hand rule a whole lot. And so at the beginning of the test, you see a whole lot of people doing this. It would've been really cool if I just filmed it and then set it to music, because like the hand ballet, as they were doing it. However, alas, I did not film it. It's just in my head with beautiful music. Right hand rule, you put your finger, you got the Sten gun. Finger points in the direction of the bullet. That's the positive charge. Positive charge is going that way. These three fingers right here go in the direction of the magnetic field, because magnetic field lines, typically, you'd never draw just one. So that's going this way. I have 360 degrees of freedom here. My fingers in the direction of the magnetic field, which is into the board. My thumb, that which, for a gun, the hammer, that which causes everything to go or move. The force in our analogy here is up. So using the right hand rule, force is up.
And the bullet's always gonna be, is always the charge?
Yes. Now it's always the positive charge. So if I had this as a negative 2 coulombs, then the bullet's going that way.
But still, like, this is referring to the
Bullet, yes.
charge.
Yeah. Textbook does a slightly different right hand rule, but it comes out to the same.
Why did we think it was up on the right hand rules? Because we have this, and you
Okay, direction of the charge or current. These three fingers, direction of the magnetic field, which is into the board.
Okay.
Thumb, direction of the force.
Okay. So,
If you're doing that, that's
yeah.
would be a negative charge with a magnetic field coming out. That's a negative charge, magnetic field going in. And let's do a different way. Pick one of them. You know, as with a lot of these things, you get to the same answer. It's all based upon what a cross product is. But as the charge comes in, I have a moving charge, therefore I have a current. It creates its own magnetic field. The magnetic field it creates, charge going this way. So, right hand rule, thumb in the direction of the current flow, like it's hitchhiking, and then fingers curl in the direction of the magnetic field it creates. So it is creating a magnetic field that is out of the board, above it, and into the board below it. Because as the current's flowing that way, charge is going out and in. Which means that I will, when it enters, I'll have additional magnetic field going into the board down here. I have an opposite magnetic field coming out there, and so my magnetic field weakens, and it will move in the direction of the weaker magnetic field, which is up.
That's more conceptual.
Yeah.
Right.
Oh, like the Sten gun.
I mean, but this is like, I'm shooting this bullet here and I'm shooting this bullet here.
Ah.
You figure out where the other fingers are going.
Oh, okay, yeah, less of a physical analogy.
Less-
Yeah. Now, do recognize it is going to curve, it's not gonna do that kind of, I guess potentially if it's not big enough, but it will curve. All right,
Are we ever gonna have to, like measure that? The curve?
no, we do not have the high energy facilities to do that.
Do they do that? Like at high energy facilities?
If you're talking, so, yes and no. So what happens is, you shoot particles in here, it hits some target. When it hits the target, you get this shower of particles coming out. Now, you need to sort of figure out what the particles are, and so one of the things they do is they expose it to either an electric field or a magnetic field to get it to curve. And so, but at this point, we're dealing with such high energy and such speeds near the speed of light, that you can't really look at it and see. I mean, when they first started out, they had superheated liquid. And superheated liquid means you take the liquid above its boiling point, but there's enough pressure applied that it doesn't boil, barely. And so if any disturbance goes through it, like a charged particle going through it, it will disturb it and you get this localized boiling, and so you'll see these trails. And at that point, you could measure, take a picture and measure it. But now, there's so many particles, as in billions of particles coming out. So they'll have a detector here, they'll have a detector here, they'll have a detector here, a detector here. So they'll notice that you got a hit here, 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 and here, and here. You got all these hits down here, and over here you got all these hits. And you got all these hits.
You kinda just guess where the light's gonna be, or not guess, but do some math or something to figure.
Oh, yeah, and then for the experiment I was part of, and they're even bigger now, once all the experimental data was gotten, I think it was 2 or 3 months, the computer was analyzing this before any person came in and started analyzing what the data actually meant, or the results meant. So what they did is now they have all these places where the particles went, and then you go through this huge math program looking for the most probable path of, is this is the same particle as that, which is perhaps the same particle as this. And you just go through a huge long process and trying to figure out which marks on one detector go with which marks on another detector.
Now, what would the use of this be? I'm just curious. You don't know yet? For fun.
You just told us.
These are unraveling the secrets of the universe.
Okay.
And you're wondering, why do we need to know what's going on in the universe?
Well, I'm just saying.
All right. This is a nice segue. I'm gonna hold off on my answer, but I will give the answer, I think, within about 10 minutes. Because it does work beautifully with what we're doing next. For all those international fans, that was an earthquake. That was not my klutziness. Let's make it even tighter. That's a good idea. Nope. Good thing I didn't stop that. We've settled. All right, so we've spent some time looking at forces on moving charges. We looked at forces acting on currents. And we talked about actually creating magnetic fields from charges. But can I get a current
From a
magnetic field?
Sure.
of course. Oh, wait, real quick, the right hand rule with that,
Yep.
that's only for which cases?
I have either a moving charge in a magnetic field or I have a current in a magnetic field.
Okay.
And if it's a current, the finger points in the direction of the current. So Faraday, Michael, sure, was playing around, experimenting. And he had a device here to measure current. It had hooked up to a wire. And so if a current flowed through it, the needle would flick one way or the other depending on which way the current would go. Over here, he had a battery. It had some sort of power supply with a current flowing there and a switch. And he noticed that when he closes the switch, the needle would flick one way and then back to zero, which he thought was odd. When he broke the contact here, the needle would flick the other way and then back to zero. So somehow he was able to create a current in the second wire based upon what happened in the first circuit. And played around a little bit more and realized that, well, if I've got my ammeter here, or probably galvanometer, and it was very narrow like that, and he opened and closed the switch, the needle did not deflect much there. If he made it wider, it flicked more. So he noticed that there was a connection between how much area there was here and how much current flicked. Well, if only there was a quantity that we had that involved area. Could it be
Epsilon sub,
what?
epsilon sub nine?
No, not epsilon.